Yes, I can hear you. Bueno, so hello guys. I want to thank you so much, David, to invite me to this
So,
presentation,
hello
give me
guys.
this opportunity. I'm
I
so
want
happy
to
to
thank you so
share what I know
much,
about car hacking.
David, to invite me
And
to.
this
So,
presentation,
hello
give me
guys.
this opportunity.
I
The
want
title of
to
my
share what I
presentation
know about car
is
hacking,
David
how I hack
to
it, my entire
invite me
life with
to
an Arduino.
this
So,
presentation,
hello
give me
guys.
this opportunity.
I
The
want
title of
to
my
share what I
presentation
know about car
is
hacking,
David
how I hack
to
it, my entire
invite
life
me
with
to
an
this
Arduino.
presentation.
So, hello guys. My name
Um,
is,
the
as
title of my
David said,
my name is Leandro Braga. I have 21 years old. I'm from Brazil. I'm a member of Car Hacking Villa and Car Hacking Village Brazil. I am the founder of Car Hacking Village Brazil. It's a new community of car hacking here in Brazil. I'm a Eco Party 2025 Buenos Aires speaker, and I don't work with cybersecurity. I'm a software engineering at Easy Access Tecnologia. It's a Brazilian company. We work with RFID systems. I'm a CTF player for Hawksec Unify. It's a CTF team here in Brazil. You usually plays Geoparty CTFs. I'm basically a cybersecurity enthusiastic, and now I'm a kernel cause speaker. So here we have some pictures. In the left side, we have this amazing picture with my friend David, Santos, and Danilo. We were in Eco Party 2025. Uh, Here it's me, Santos, Danilo Erazo, Davi, and my beautiful girlfriend that was with us traveling. In the middle, we have a picture with the car, me and the car hacking village A28C. A28C, it's the Brazilian conference in 2024. And the right side is the car hacking villa 2025. Have the guys from Calpatec, me, Gaston, Daniel Erazo, and Lupin. In the top, we have my CTF team, the Hawksec Unify. We were in 828C 2025, 2024. And finally, my co-workers, the software team in Easy Access Tecnologia. So this presentation, we have an agenda. First, we'll talk a little introduction, then tools and dependencies, documentation, finding the CAN bus, CAN sniffer setup, sniffing, injecting, a conclusion, then future projects that I will work. So let's start. First, my objective with this presentation is to show you guys a real example of using CAN bus reverse engineering to control your car functionalities, your car features, and teach you how you can reproduce it with a low-cost setup, with a low-cost device. And to make you think, how can I apply this logic, this what you will learn here to hack other functionalities or to explore other weaknesses in your car? And the main device I will use here is where are in Arduino Uno R3 and the MCP2515 CAN bus module. I will talk more later. And important attention. This project was performed on a 2012 Volkswagen Polo. The process will likely be different for other cars, but the core principles may be similar. Always proceed with caution. So the logic of CAN bus reverse engineering is the same for all cars, but some specific stuff like bitrate, like the physical place in the car, that's it's different for different vehicles. So let's start explaining some basic stuff about CAN bus and other topics to help you guys to understand all the presentation. First, we need to talk about CAN. CANs means controller area network. So if the car was a body, like a human body, the CAN bus will be the nervous system. So all the devices is connected to the CAN bus. So the CAN bus is the network. These networks allows them to constantly communicate and share information with each other over a simple two-wire system made up of a CAN high and a CAN low line. So every device, every node of this network is connected with each other with these two wires, the CAN bus, the CAN high, and the CAN low. So here below we have a picture, like a diagram showing a basic example of a CAN bus network. So we have three CAN devices. For example, CAN device 1, 2, and 3, and every device is connected with each other. And when one device send a message, every other node will receive this message. For example, if the CAN device 1 send a message, the CAN device 1, 2, and 3 will receive the same message. So that's why we need to understand the CAN frame. The communication over the CAN bus is done via CAN frames. Below, we have a picture is a standard CAN data frame with 11-bit identifier, which is the type used in the most cars. So, and we have the other type of CAN frame with the 29-bit identifier, but is identical except the longer ID. So the CAN frame is identical, just in the size of the identifier. So we need to know that the CAN ID and the data are highlighted. These are important when recording CAN bus data, as we'll see below. So in this picture, we can see the CAN ID and the CAN data highlighted. That's all the important stuff we need to know when we are CAN bus reverse engineering. The other, like the soft, the RTR, the CRC, AC, and EOF, we don't need to know about it and to in this type of project. We just need to know that every CAN frame have an ID and a data. The CAN ID is to represent who is sending, which device, which node in the CAN bus is sending the message, and who needs to receive the message. And the CAN data is the message itself. Then we need to know some physical stuff. The signals. The CAN bus works with differential signals. Can transmit data by using two complementary signals on two separated wires, the CAN high and the CAN low. Make it more resistant to noise and interferences, because the car have a lot of noise, have other devices connected, so have a lot of interferences. And the receiver interprets the data by measuring the difference between the voltage of the two wires. So he measured the difference between the CAN high and the CAN low. And any noise that affects both wires equally is considered out. For example, we have the two logics, the logic 1, recessive, and the logic 0, dominant. So in the logic 1, both wires are at the same voltage, for example, 2.5 voltage. So the difference between 2.5 and 2.5 is 0. So this will result in the byte 1. They both are in the same voltage. The otherwise, we have the logic 0. The wires have a clear voltage gap. For example, the CAN high is in 3.75 voltage and the CAN low at 1.25 voltage. So we have a clear voltage gap. So the difference between these two voltages will result in a number different than 0. So this will result in the byte 0. So here we have a picture showing a basic example of a CAN bus, CAN high and CAN low wires voltage. So when the CAN high is affected, the CAN low is affected at the same. So the difference will be the same in the two types of voltage, and all the noises will be cancelled. Then baud rate and bit rate. In this presentation, both bitrate and baud rate are used to measure the speed of data communication. We are using serial devices, so we need to control and know the specific speed of the data communication. With so without it, we can't read and write data. So to successfully read and write data on the CAN bus, it is crucial to know and use the correct bit rate. In the CAN bus, you use the bit rate. All devices on the CAN network must be set to the same bit rate to ensure reliable communication. And we will use the baud rate for Arduino communication. So in the Arduino, we need to set a specific baud rate. It is essential to use the same baud rate on both the Arduino and the device reading the data to ensure the information is received correctly. So in our Arduino, we need to set a specific baud rate. And to read the information that's coming from the Arduino, we need to specify this baud rate in our computer to read the data. Finally, SLCAN. SLCAN is a protocol that converts CAN bus into serial communication. So it's basically a translator. We receive CAN bus and translate that to serial line communication. So commonly used to connect a computer to a CAN bus via USB port, for example. The protocol transmits CAN data as ASCII2 characters over a serial connection. So basically translate the voltage, the zeros and ones to ASCII2 characters that we can read, interpret, and sniff and other stuff. The SLCAN protocol acts like a translator, converting the serial data from a USB connection into CAN messages and vice versa. So let's talk about tools and dependencies. This project was performed with an Arduino Uno R3, as I said. In Arduino, you need to use a sketch. I use the slcan.in sketch to enable CAN over serial communication. As I said, we need to translate the CAN bus to serial line communication. Then I built the slcan.in sketch, that's the code that translates that. And a library from AutoWP called Arduino MCP2515. This library enables us to communicate with the MCP2515 module. Uh, I need to create some terminal scripts. I use the CANutils macOS library, but if you can use the normal Linux library CANutils, the process will be basically the same. The CANutils macOS library, I create that because I use a macOS and the MacBook don't have CANutils in the kernel. It's just for Linux devices. So I need to implement by myself a CANutils. Is basically a copy from Linux CANutils, but using Python CAN. So the process will be exactly the same in the two libraries. And we have the picture of the two devices I use it for this project. In the left, we have Arduino Uno R3. It's a simple robotic device, and MCP2515. This guy works like a translator, but from the voltage of the CAN bus to numbers. So the MCP2515, we connect directly this part, the CAN high and the CAN low to the car. We need to connect directly. And the car message will be sent to this guy, and he translate that to numbers and send to the Arduino. So here we will start the process of the CAN bus hacking itself. We need to find a documentation, a useful documentation. So uh, every car have a wiring diagram and a repair manual. It's documents to every car that contain important information. In this project, in my car, the Volkswagen Polo, I found the wiring diagram, which mentioned to me four critical pieces of information. First, the powertrain CAN and the comfort CAN. My car had two CAN bus networks. The powertrain controls the engine, the brakes, the gears, and that stuff, and the comfort CAN control the windows, doors, lights, and other stuff. I found it too that my car have the CAN bus wires colored. The CAN high wire color is orange black, and the CAN low wire color is orange brown. In my car's dashboard, the instrumentation cluster have the CAN bus wires. I found all this information in this document, the wiring diagram. So that is too important to find these documents, because without it, we like in a black box. We don't know the speed, communication, and the color of the CAN bus wires. So it's too hard to like work like a brute force and try every wire possible inside the car. So, and here we have image showing it's like a print, a screenshot in the document that showed the CAN bus wires colors. So the CAN low color is orange brown, and the CAN high color is orange black. So let's go to the physical search. We need to find the CAN bus. As we saw in the wiring diagram, my instrumentation cluster, my dashboard have the CAN bus wires. So I need to remove my instrumentation cluster. So following the documents, I removed the dashboard searching for the CAN high and the CAN low wires. So in the left side, we have a picture of my instrumentation cluster. Then I remove it. And when I remove it, I found two main connectors, a black one and a green one. So I identified two main connectors, and I located the target CAN wires in the green connector. So we can saw the green connector here, and behind that we have a lot of wires, and we can see the CAN bus wires right here, the orange black wire and the orange brown wire. Then we need to check the wires. Basically, I use an oscilloscope and tested each pin until I found the signals for the CAN high and the CAN low, because I don't know exactly what wire goes to what pin out. So I need to use an oscilloscope and try every pin out possible until I found the signal that looks like a CAN high or a CAN low signal. That's important. That's why you need to know about differential signals, because here we saw in the oscilloscope the signals that look like CAN high signals. So we can see the average voltage is 3.5 voltage, and we can see that have a normal voltage and the top voltage. So it's going to up, it's going to top, and that's CAN high. And in the right side, we have the same signals but to down. So, and the average voltage is 2 voltage. So we can see, we identify it right here, the CAN high and the CAN low wires. After we found a physical place with the CAN bus wires inside the car, we need to prepare our CAN sniffer. So we need to prepare the Arduino. We just need to get the Arduino, connect to our computer, and upload the slcon.ini sketch with the Arduino MCP2515 library. Then we need to connect the hardware. The Arduino and the MCP2515 need to be connected according to this diagram. So the MCP2515 communicate with SPI protocol. You don't need to know about it. You just need to connect it correctly. So the SPI pinouts in the MCP needs to be connected to the SPI pinouts in Arduino. And a tip to test if your Arduino MCP2515 setup is reading data, you can open your Arduino IDS serial monitor and set the baud rate to 115,000 into 100. If you can see any data being logged, congratulations. You are connected the car and you are able to read the CAN bus data. So we already found the CAN bus wires in the car, already set up our CAN sniffer, and we are connected to the car and we are able to read the CAN data. Now we just need to sniff the data. From this point on, I use the Python script from CAN Nutu's macOS library to interact with the CAN bus. First, we need to set up Python virtual environment. So the Kernel macOS library was built in with Python. So we need to set up the Python virtual environment to download all the dependencies and that stuff. First, we need to run Python 3 dash m VM to create the virtual environment folder. Source VM being activate to activate this virtual environment. Then we run two commands from Python, pip install upgrade pip to upgrade the pip command, and pip install dash r requirements dot dash txt to install all the dependencies. Next, I use the can sniffer interactive.py script to sniff the can data from the car. Uh, just running Python can sniffer interactive.py dev cu usb serial. Uh, you need to pay attention here because this path will likely be different in your machine because this path dev cu usb serial is about my Arduino. So when I connect my Arduino in my macOS, the path of the media from the Arduino is this one. But when you connect your Arduino or your SP32 in your machine, the path will be different. So with the sniffer running, the hard part begins. We need to interact with the car functionalities like pressing buttons, opening doors, unlock doors, and observing changes in the can sniffer output. After an intense search, I found something interesting related to can ID 470. So when you are connected and sniffing, we can read all the can messages in your car. Then we need to work like physical. We need to press in buttons, move your steering wheels, pressing your pedals, open doors, open windows, and find a pattern in the CAN bus communication. Uh, Here I will show a demonstration in my car. Here is a video showing me. I'm sorry, I'm not a content maker, so the video is not good. But basically, we have the Ken sniffer running right here, and each line is related to a Ken ID. So the first line, for example, is about Ken ID 050, and we have the data of Ken ID 050, and we need to interact in our car and read and find a pattern in the Ken data. So, for example, I'm inside the car and I'm pressing the hazard light button, the emergency light button, and I can see the CAN ID 470 changing the data. So when I press the, sorry, uh, when I press the emergency light button, the emergency lights go on, and I can saw the difference between when the hazard light is on and when the hazard light is off. Here we have some pictures to improve the visualization. So to get clear view of just one ID, for example, you find something interesting related to ID 1. In my case was the ID 470. Then I can use the candump.py tool that allows me to filter for one specific can ID. And for example, with the hazard lights, with the emergency lights off, I can see the can data, the first byte of the can data 80808080 all the time. So I run the Python can dump command passing the path of my Arduino, uh, change the backend to SLCAN, the bitrate of my car. We need to know it because if I pass the wrong bitrate here, I was unable to read the CAN data, and filtering by the correct CAN ID. For example, the 470 CAN ID. Then each line is only about the CAN ID 470. And when my hazard light is off, I can see the first byte 80. And when the hazard light is on, the first byte changes to 8B 88, 8B 88. So we found a pattern, un padrón, and we can explore that. It's the same logic for every car functionality. So to control the hazard lights, I use the can send command. It's another tool from Knutu's library. It's a script to send my own can message into the CAN bus. So the command to turn the hazard lights on is Python can send, pass the Arduino path again, and the can data. So the first, we need to pass the can ID, for example, 470, hashtag, and the can data. So I send the first byte 8B because I know when the hazard light is on, the first byte is 8B. Then I send 8B0000FF02, and the hazard light that was off goes to on, and it worked. Then I send the command to turn the hazard lights off. It's like the opposite. So Python can send my Arduino ID, my Arduino Uno path, and the can message. I just need to pass 470 can ID, hashtag the can data. We know that when the hazard light is off, the first byte is 80. So we just need to pass 800000FF and 02. Then I will show a demonstration of CAN bus injecting. So that's my car, and you can see the emergency light is off. The hazard light is off. And my computer are connected to my instrumentation cluster, and we can run the Python can send, and here we have the can message 470 8B0000FF02. We know when the hazard light is on, these messages are inside the CAN bus network. So we just send the message. Message send, and the hazard lights go on. We can see the emergency lights turn on. Now we do exactly the same to turn the hazard lights off. Just send the message 80. So again, 470 CAN ID, sending the 80 byte. Message sent, and we can see the emergency lights going off. So you need to understand the pattern. You need to look the pattern in your canvas by interacting with your car and found when something is up or something is down or on, we can see a pattern. So imagine in your car, your side light can ID is one, for example. So when your side light is on, your can message from can ID one is one. And when your side light is off, your can ID message from can ID one is zero. You find a pattern. And you need to find this pattern by interacting in your car functionalities, in your car features. So that's the hard part. That is the CAN bus reverse engineering. Interact with your car and read the bytes from the CAN bus and find the pattern. So, a conclusion about this project, this presentation showed a basic example of CAN bus reverse engineering to help to the understanding, but you can apply the same logic and steps to control and hack other car functionalities and build your own project. So you can apply the same logic to other car functionalities like your engine, like your doors, like your windows, your brakes, your gears. You can apply the same step-by-step guide and just need to interact with other car functionalities and find the pattern of these functionalities. You can find the Kernel macOS library and this slcan.in sketch code in my GitHub repository. It's open source. And for a detailed guide on this project, please visit my project page. So the code is available in my GitHub repository, and the step-by-step guide, like a documentation, is available in my website, Car Blank Hack. Finally, this project was heavily based on and inspired by the work of Faraday. Faraday is an Argentina company that works with security researching, pen testing, and that stuff, all about cybersecurity. And they posted a project how to unlock a door with Doogie. Doogie is like a code that run inside an SP32 or a Raspberry Pico that allows you to communicate with your CAN bus too. Their content is amazing, so please check it out. And to finish, some future projects. I'm currently working in a project to play Mario Kart inside with my car. So the car I'm using is a Ford K, Ford K. I don't know how can I say it in English. Um, to control, we need to make again a CAN bus reverse engineering and translate the CAN bus message into inputs inside the Mario Kart game. So I need to go inside my car and connect by the OBD2 connector, the diagnostic connector, and make a CAN bus reverse engineering again and understand when the steering wheel is changing and when my pedal is changing, I can translate that to the input inside the game. Then I can play Mario Kart inside my car. That's it. That's my presentation. Thank you so much for the attention. Here we have my social media. If you want to contact me, please, we can talk about whatever, some cybersecurity stuff, and I'm open for questions. What are the limitations of using Arduino for automotive security testing compared for professional diagnostic tools? That's a good question. The limitation of Arduino Uno is you need to build by yourself the message. So when you use a professional diagnostic tool, you probably connect it to the OBD2 port, the OBD2 connector. And the OBD2 have a default, have a standard protocol. So every car OBD2 connector have basically the same message and the same ID. Is like a HTTP service, like a known protocol. But when you are using your device, like an Arduino, like an SP32, you need to make this CAN bus reverse engineering. So, for example, if you want to know what CAN ID is related to your window, we need to read. And you need to implement by yourself in the code, in the firmware inside the Arduino or the SP32 and send to the SP32. So it's kind of harder, but you have a infinity possibilities to work. You can the professional diagnostics tools only works with diagnostic, like clear some message, some error message and other stuff. But when you are using your own device, you can do whatever you want. I don't know if it was clear. Thanks so much. Thanks so much, Levi, for the invitation. I'm so happy to be here. I'm so happy to help the community, and we can keep contact, and we can be together in others conferences. And I hope to, when I finish the project to play Mario Kart, I will show here again. It will be a pleasure. Bye bye.